Hello students, welcome to EPG Pathshala. I am Dr. Varun Vyas from Department of Physics and Astrophysics from University of Delhi. Today we are going to discuss about the module Scanning Probe Microscopy from the paper Measurements and Instrumentation. In this module, we will study about scanning probe imaging methods. In this surface scanning technology, we will study about scanning tunneling microscopy, where the basics of imaging, instrumentation, and various imaging modes will be studied. And in atomic force microscopy, we will study about basics of imaging, instrumentation, and various imaging modes. Scanning probe microscopy, that is SPM, is a branch of imaging techniques that scans the surface with a very sharp probe and whose contact diameter may vary from the size of few atoms to tens of nanometer. This imaging technique is considerably different from TEM, SEM, and other optical methods. In these imaging methods, source is quite far from the specimen. It may be an electron gun for TEM and SEM, and optical imaging, it may be a tungsten halogen lamp or an LED. Therefore, it is the scattering of the light and electrons that produces an image of a specimen. Here, it is not possible to get a surface profile of the sample that can be used for measuring surface roughness and study 3D shapes and size of micro to nano-sized object. Scanning probe microscopy can be broadly classified into scanning tunneling microscopy, that is STM, and atomic force microscopy, that is AFM. In STM, a tunneling current between atomically sharp probe is used for scanning the surface, whereas in AFM, a 100 to 200 micrometer long cantilever with a sharp silicon nitride or silicon crystal tip is used for scanning the specimen. Let us first study about scanning tunneling microscopy. Thereafter, we will study about atomic force microscope. Scanning tunneling microscope. The scanning tunneling microscope was developed in early 1980s at IBM Research Laboratory in Switzerland. The microscope was developed by Benning and Roher, for which they were awarded a Nobel Prize in Physics in 1986. STM consists of small, sharp conductive tip that scans across the sample of interest. The tip has a diameter of few atoms only. The separation distance between the tip and the surface is close to 1 nanometer. At this small distance, a quantum mechanical tunneling current can flow between the atoms at the tip and the surface. Before we move ahead, it is important to understand the concept of tunneling from classical physics point of view. For electron to travel from one state to another, they must cross a barrier potential. That is, they must have sufficient energy to move across a barrier. This is similar to a person trying to carry a heavy load over a hill. In quantum physics, the same can be achieved by digging a tunnel through a hill. Hence, comparatively less amount of energy is required to move an object through a mountain or a hill. In our case, starting point of the movement of electron can either be tip or sample. Here, the barrier is air or vacuum, that is, conditions under which imaging of the sample is being performed. Tunneling condition. For electrons to move through the barrier of air or vacuum, it should satisfy energy-time uncertainty relation, that is delta E dot delta T, which is greater than equal to H, where delta E is the uncertainty of energy, delta T is the uncertainty of time, and delta H is the Planck constant. From the above equation, one can derive it to tunneling condition, that is d square into E bar. This is less than equal to h square divided by m. This is equation 1, where d is the width of the potential barrier, E bar is the height of the energy barrier, and m is the mass of the electron. To further understand how tunneling condition gets satisfied, let us assume tip is d distance from the substrate, that is 10 raised to power 9 meters. The E bar, that is the height of the energy barrier, is given by the work function, which amounts to few electron volts, that is 10 raised to power minus 18 joule. The left side of the tunneling condition can be written as d into root of E bar. This is equivalent to 10 raised to power minus 9 meters into root of 10 raised to power minus 8 joule. This is equals to 10 raised to power minus 18 joule second kg raised to power minus 1 by 2. This is equation 2. And from the right side of the tunneling condition equation, we get h into root of 2 by m. This is equivalent to 7 into 10 raised to power minus 34 joule second into root of 2 into 10 raised to power 30 kg raised to power minus 1. This is equivalent to 10 raised to power minus 18 joule second into kg raised to power minus 1 by 2. This is equation 3. From the above calculated rough estimate, one can understand the electron tunneling in STM by merely considering the uncertainty principle. One should note that electrons may not only tunnel from the tip to the sample but also in reverse direction. This is demonstrated by an energy diagram in figure 2. Here it is assumed that both tip and the sample have identical work functions at an applied voltage of U. The electrons on the one side of the barrier, that is air or vacuum, tend to have more energy than the other. The slope of the potential is drawn with the slanting potential barrier. Working principle. In STM, there is a small metal tip that is placed at a distance of 1 nanometer, that is few atomic layer above the sample. The tip is attached to a scanning device that moves in a rastering manner above the sample. This scanning device has 3 piezos X, Y, and Z that control the mobility of the tip in the 3 dimensions. During rastering, tip scans the sample in x-axis and moves one line at a time in y-axis. Therefore, a tip scans the surface faster in x-axis direction and is comparatively slower in y-axis direction. The ZA piezo controls the position of the tip above the sample. The basic design of the system is given in the figure 3. A small potential of UT is applied between the tip and the sample. The tunneling IT that is usually in microamperes, flows through the circuit. All the three piezos are connected to a feedback loop system that controls the position of the tip over the sample in real time. The magnitude of current between the sample and the tip is constantly measured. It is important to note that only electrically conductive samples can be examined with STM. To get the best resolution, one should get a one single atom at the very end of the STM tip. The conduction electrons with a metal are able to move almost freely, though they cannot leave due to the attractive force of the positively charged core. For electrons to leave the sample, work must be done, which is known as work function phi. Quantum physics allows us to estimate this movement of electron between the sample and the tip. The tunneling current depends upon the distance between the tip and the sample, and this is given by IT is equals to C1 into UT into exponent raised to minus C2 into root of phi into D. This is equation 4. The tunneling current decreases exponentially with increase in distance. The constant C1 is dependent on the electron densities at the tip and on the sample. The exponent contains the another constant C2 and phi is the work function of the metal. If the tip and the sample have different work functions, then the mean value is used here. Typically, working parameters are IT is equals to 10 raised to power minus 9, UT is equals to 100 millivolt, phi is equals to 5 electron volt, and D is equals to 10 raised to power minus 9 meter. Two operation modes. STM can be operated in two different modes. First is scanning at constant height, that is, the tip is probing the surface in a straight line and at the same time tunneling current is recorded. Second is scanning in constant current mode, that is, tip probes the surface in a way that it keeps the tunneling current is kept constant. The change in tip height gets recorded here. In easy scanning, constant current mode is used. For imaging in constant height mode, the controller should be adjusted to move slower so that it is able to follow any gradual changes due to thermal expansion effects. Atomic force microscope, that is AFM. An atomic force microscope is a highly versatile instrument that was developed in 1986 by Benning, Quate, and Gerber. It was an attempt to develop a technique that can be used for measuring non-conducting samples with atomic resolution. Earlier, with STM, only conductive samples could be examined, but with development of AFM, polymers and other biological non-conductive specimens could be imaged with high resolution. As the name implies, this technique is dependent on the intermolecular forces, that is, van der Waals, electrostatic, etc., between the tip and the sample. Here, AFM probe is on a non-conducting stage and there is no flow of current between the tip and the specimen. Operating principle and the instrument design. Various components of AFM are shown in figure 5. The main difference in operation of AFM as compared to STM are a cantilever of known force constant with silicon nitride or silicon crystal tip is used for scanning the sample instead of a sharp metal tip. A tip has a nominal diameter of 10 to 40 nanometer. B. XYZ piezo's can be mounted either on the cantilever stage or sampled stage, whereas for STM, piezos are preferred to be mounted to a metallic tip holder. C. The motion of the cantilever is detected by deflection of a laser from the backside of the cantilever. The movement of the reflected laser is detected by a photodiode, and the net difference in the signal from the four quadrants of a photodiode is used to develop an image of the scanned sample. Probe. An AFM probe is micro-machined cantilever that has sharp tip at its one end, which is brought into interaction with the sample surface. Each probe has different specifications and shape. The cantilever can be a V-shaped cantilever or rectangular, providing a low mechanical resistance to vertical deflections and high resistance to lateral torsion. Cantilevers typically range from 100 to 200 microns in length to 10 to 40 microns in width and 0.3 to 2 microns in thickness. Integrated cantilevers are usually made from silicon crystals or silicon nitride. They are characterized for their force constant and resonant frequency. The probe of the appropriate specification should be selected while studying the sample. Additionally, an optical detection system and electronics for the management of the scanning procedures and data acquisition are necessary. Beam deflection detection. To detect the displacement of the cantilever, a laser is reflected off the back of the cantilever and is collected in a photodiode. The diode is divided into four parts as seen in figure 5. When laser is displaced vertically along the positions top A1 to A2 and bottom B1, B2, there exists a bending due to topography that can be written as vertical deflection is equal to A1 plus A2 minus B1 plus B2, whereas horizontal deflection that produces a torsion due to friction, that is a lateral force, when cantilever moves across the surface, can be defined as horizontal deflection is equals to A1 plus B1 minus A2 plus B2. Mode of operations. The two most common mode of operations are contact mode and tapping mode. Figure 6 illustrates the mechanism of action of the cantilever during the two imaging modes. Contact mode. In so-called contact mode, tip makes a soft physical contact with the surface of the sample. The deflection of the cantilever dx is proportional to the force acting between the tip via Hooke's law, that is, F is equals to minus K into X, where K is the spring constant of the cantilever. Here, tip either scans the sample at a constant small height above the surface or under the conditions of a constant force. In the constant height mode, the height of the tip is fixed, and in the constant force mode, the deflection of the cantilever is fixed. The motion of the scanner in z direction is recorded, that gives 3D profile of the surface. With contact mode AFM, even atomic resolution images can be obtained. For contact mode AFM imaging, cantilever should be soft, that is low force constant less than 10 Newton meter, enough to be deflected by very small force, and should have high enough resonant frequency to not to be susceptible to vibrational instabilities. Silicon nitride tips are used for contact mode. In these tips, there are 4 cantilevers with different geometries resulting in 4 different spring constants. Tapping mode or intermittent contact mode. The force measured by AFM can be classified into long-range forces and short-range forces. The first class dominates when sample is scanned at large distances from the surface, and short-range forces can be van der Waals force and the capillary force due to the layer of water often present in an ambient environment. When the scanning in contact mode, the surface, the short-range forces are very important, in particular the quantum mechanical force, that is Pauli's exclusion principle forces. In tapping mode, AFM cantilever oscillates close to its resonance frequency. An electronic feedback loop ensures the oscillation amplitude of the cantilever remains constant, such that a constant tip-sample interaction is maintained during the scanning. Forces that act between the tip and the sample will not only cause a change in the oscillation amplitude, but also change in the resonant frequency and the phase of the cantilever. The amplitude is used for the feedback, and the vertical adjustment of the piezo scanners are recorded as height image. Simultaneously, the phase changes are represented in the phase image, that is topography. The advantages of tapping mode are the elimination of a large part of permanent shearing forces and the cause of less damage to the sample surface, even with stiffer probes. Different components of the sample, which exhibit difference as the adhesive and mechanical properties, will show a phase contrast and therefore even allow a compositional analysis. For a good phase contrast, larger tip forces are of advantage, whereas minimization of this force reduces the contact area and facilitates high resolution imaging. So, in applications, it is necessary to choose the cantilever of appropriate force constant. For tapping, force constant of cantilever generally greater than 20 to 40 Newton per meter, silicon probes are used primarily for tapping mode applications. So students, let us summarize what we have learned in this module. In this module, we studied about 2 kinds of scanning probe imaging techniques. First, we studied about scanning tunneling microscopy, where we briefly discussed about the phenomena of tunneling. Thereafter, we studied about 2 imaging modes. One is constant height mode and another is constant current mode. Second technique we studied is atomic force microscopy, where we studied about the basic design of the instrument along with 2 kinds of imaging mode, contact mode and tapping mode.